times that this will be my last lecture. And there will be one more in a special environment in the scope of a seminar I will have in 2 weeks. The seminar in numerical methods. That's, I think, the title of the seminar. And I will speak on the method of Newton. A small contribution of myself about the convergence of the Newton process. And I think that fits well into this course. It will be just 1 hour. It is in Thursdays at noon. I'm not quite sure where exactly we did stop last time. So maybe you help me. Huh?
You said
we defined the Fourier transform was defined or not? Well, just, but this was a sort of preview. Which we yeah. Well, I think we define the Radon transform as F phi p to be equal as integral over R yes. F P theta plus S theta orthogonal ds where theta is cos phi, sin phi, and theta orthogonal is minus sin phi cos phi. That was the definition. And we just proved some simple facts. We proved, yes. Yes. I think we proved the following identity. Integral over R, RF, phi P, HP dP being equal to integral over R2 f of x h theta orthogonal times x scalar product with x dx. We also proved that this transformation is continuous in L1. I think that's what we have proved. And now it is the time to see what's bad with the radon transform and why. And that's not quite direct. You should get the impression or conviction that the inverse of this map is not continuous in any reasonable topology. It is, so if you have some functions that you can construct functions fn not converging to 0 such that Rfn converges to 0. Something like that. But even more in this sense. So, to this aim, we have to establish the connection of the radon transform with the Fourier transform. So I will define Fourier transform in R2 as f small f of psi being equal to 1 over pi integral R2 f of x e to the minus ex psi dx. And also the one-dimensional transform, which I will define with f1. We will use it on a special class of functions just on those g, f, p. So phi f1 of g taken on the place phi p prime is equal to 1 over square root over 2 pi integral g phi p e to the minus e p p prime dp. This is the standard one-dimensional Fourier transform with respect, in this case, to the variable p. So yes, you do it just in one variable. You leave the other constant. Now, once we know that, we can also define this as a f hat of psi. This is a standard Fourier transform into dimension of our input function f. This is some partial Fourier transform. So those two come into play with R. So the identity I like to prove is the following. 1 over square root of pi f1 R f phi p prime is equal to f hat p prime theta. You shouldn't forget that it is a shorthand here. Theta is a function of phi. So to prove that, I will use this identity and take H of P p to be equal to 1 over 2 pi e to the minus I p prime. So then 1 over 2 pi integral over r phi sigma e to the minus p prime d pi is now equal to 1 over 2 pi. Now I'm using this. 1 over r dp 1 over r ds f p theta plus s theta orthogonal e to the minus I p prime. I just substituted into it. But now comes the same trick. We transform the variables s and p back to x1 and x2 in the same way as we did before, because this is now a simple integral over R2, because s and p are two orthogonal variables. So when we come back, then it is now 1 over 2 pi integral over R2 f of x e to the minus e p prime. Now I have to substitute this scalar product. That means x1 cos phi plus x2 sin phi. This is a scalar product. Yes. And then this is equal to 1 over 2 pi integral over r square f of x times e to the minus I p prime times theta scalar product with x. The x. Now the formula should be proved. We just have to look. Yes. Well, this is exactly f hat taken at the place theta yes, theta times x. But now, what is theta times x? We have now to transform back. P yes. Now that's it. You should put this is you have scalar product with P prime times scalar product theta times x is equal to x scalar product to P prime theta. And that's what comes in the Fourier transform, so that's it. So that's one part of the integral. And the other part is just this here. Well, next, when we are taking Fourier transform, then the natural environment for the Fourier transform is not L1, but L2. This is where the Fourier transform is a unitary operator. That's one point. The second point, in studying such things, everywhere you will stick to some spectral decomposition. And spectral decomposition can only be made in a Hilbert space. That means you have to have some self-adjoint operators or self-adjoint matrices which allow spectral decomposition. So we have to look in this R, well, in L2. So what is R, F, G? That means scalar product. Where? On some L2. Where? Which variables are there? Phi and P. That's the scalar product, the natural one. And what's the next thing to try to find that's the adjoint of this operator. If there is such. Maybe it's just the same, R equal to R star. Well, that will not be true, the case. But let's look at the formula for this adjoint. Well, now we get some little troubles. Which class of functions will be our f and g? If f and g are L1, we know if f is from L1, then Rf is also from L1. And so if take both f and g from L1, this integral need not to exist. If you multiply two L1 functions, you just take something like that in one dimension. This is L1. Converges, but you square it, then you get minus 2 alpha x over x. This is not integrable. So we have to restrict ourselves to something better. So take, for example, f from L2 and g also. Now this L2 and this L2 is not the same, because f is defined on R2 and g is defined on the Cartesian product of the circle and L1. So these will be corresponding L2 spaces. This will be R2, and this will be over 0 to pi times R. And to be simple, let's take them with compact support. This is not unnatural because in our model, anyhow, the whole thing, the body is a bounded set. So the function f has typically compact support. So let's take both of them. So let's compute this integral now. Y equals to R f g for those functions f and g we define there. That means we have to compute them in the L2 of this, because Rf is anyhow a function of phi and p, and g will be supposed also a function of phi and p. That means 0 to pi d phi integral twice f p theta plus s theta orthogonal g phi p d s dp. That's the definition. That's the scalar product. I remind you that our Hilbert space is real. So there is no complex conjugate in the scalar product. So now this integral, of course, now exists, because we have two and we can make the same coordinate transformation once more. X to PS. And we get integral or 1 to 2 pi d phi integral over r square f of x. Now we have g of phi theta times x dx. That's it. So, this gives us f r star g, where r star is equal to g. Now on the place x being equal to integral over d phi g phi theta x. And that's the definition of the adjoint. In particular, the operator R star R, if exists, or where exists, will be positive semi-definite. Positive semi-definite, just as any matrix of this type is positive semi-definite. And which is more, we will, well, let's just ask where this operator is certainly defined, where it exists. If I restrict myself here not only to L2 functions with compact support, but take just continuous functions with compact support, then all those operators R and R star preserve these subspaces. So this is then defined at least on the defined at least on F continuous with compact support. I'm not very careful about which spaces we take here. Why? Because all such spaces are dense in functional spaces which are really relevant for the theory. So once you establish an inequality or equality on a dense set, you have it automatically left up. So this will now enable us to establish one so-called reconstruction formula. Yes. I will not do that. Which will also give us some information about the inverse. Because the inverse of R is the object we are interested in. And this formula reads, one over 4 pi R star lambda R F is equal to F for any F from C01. That means functions with compact support and continuously differentiable. Even those functions are dense in any reasonable functional space we will be working with. Now, what's lambda? Well, lambda is a sort of lambda is formally defined as square root of minus d2 over dp squared. So we take the second derivative with respect to p, and this is of course an operator, a map. And the second derivative is also a map. And with the use of the Fourier transform, you know that this, in the Fourier transform, if you take f1, that is the Fourier transform in the variable p, then you know that to minus d square over dp square corresponds what in the Fourier picture? The multiplication by p star square. It's easy. That's the simplest thing one knows about the Fourier transform, that the derivatives go to the polynomials and vice versa. But now, when we have the polynomial, then we can take functions of it, for example, square roots, and then transform back by the Fourier transform. And that's the definition of the operator. So let me be more formal. If I have a function g, I still keep my phi because these are the functions I have. And it is defined as 1 over p integral over r g Fourier transform of 1 over g phi p prime e to the I p p prime d p prime. That's what it is. This is now the inverse of the Fourier transform. The Fourier transform had a minus e pi p prime, and now we have a plus. It's the only difference between the operator. It's the inverse, just a sign on the exponential function. So now, what is now minus dg over dp squared? It's the same thing, but only p squared times this. We just differentiate twice. And what's then lambda g phi p, which I define as square root over minus d square over dp square on g vp. Well, that's the definition. What's this? This is a sort of pseudo-differential operator. Pseudo-differential operator. It's a technical name for them. These operators have quite a lot of properties which are analogous to differential operators. But there is one big difference. They are not local. If a function, say this g, has a compact support, then any derivative of it will also have a compact support. That's trivial. But a pseudo-derivative will not. So now I have established what this formula says. Before proving it, let's discuss it. Well, this is in fact our G. That's the map. So this formula gives me a possibility to compute back my F if I know what the G is. I just have to multiply it by lambda and R star. So that's why this is called a reconstruction formula. It is an implicit way to give the inverse. Well, if you recall some linear algebra, and you know this operator is positive because it is you are multiplying by a positive function. So you can also define the lambda 1/2 by putting this p 1/2. It's easy. And you see these are functional calculus. You can define powers of such operators, and they have the same properties as standard powers. Well, then I can write down this as something like that. 1 over 4 pi r star lambda 1 half r times square root of 4 pi is equal to 1. That means that this, if there is justice in this world, then this over 4 pi is unitary. Star times this gives 1. This operator preserves norm. But now suppose that R has a bounded inverse. And that's what it's all about. We have the map F goes into R, F equal to G, and we would like to know if, or whether F depends continuously on G. That's the question. And that means, is the operator R to the minus 1 continuous? Which is the same thing for a linear operator as to be bounded. So R to the minus G, is it less or equal than some constant times G? In any reasonable norm. Well, in finite dimensional space, all norms are equivalent. Not so here. But we have reasonable norms, L2, LP, Sobolev norms, and so on. So now, let's look now in the Hilbert space, in L2. If this would be, if the R would be continuous, let's call U, then U times U to the minus 1 times R would give 1 over 4 pi times lambda 1 half. And that would be a bounded operator. And that's not the case. Why? Because we have an explicit formula for this operator. The boundedness of the operator is invariant whether you look it in the original space or in the Fourier picture. It is just unitary transformation from L2 into L2. But P, multiplication by P, is not bounded. This operator works like the following. You have a G of phi pi. P is mapped into P times G phi P. And this multiplication goes from 0 to infinity. So it's easy to take functions which have compact support and a unit norm, and support is squeezing to 0, and this will go to 0. It's trivial. You multiply this, you take functions like something like that, but with fixed L2 norm, and this will go to 0, because P is killing it. I'm now appealing to some knowledge of functional analysis here, which I hope you have. So this is unbounded. The inverse is unbounded, but P itself is also unbounded. So it is both unbounded together with its inverse. So the same holds then for lambda. So that means at least that R cannot be a bounded operator, at least not in the Hilbert space. But it is a negative negative conclusion from this formula, but there is a positive one, that you can reconstruct it. In fact, even from this formula, you can see that the operator R, well, its inverse, if it exists, is not bounded. But does it exist at all? Is this operator R injective? That's also a question. Well, this formula shows it cannot be, it is injective. If it would be, there would be some reasonable f where it would be 0, then that couldn't fall. So it is injective. R is injective. It is not full proof of it. A better proof can, I think, be got here. If we would have R on F to be equal to 0, then F1 will be equal to 0. And that means that F hat is equal to 0. But the Fourier transform is injective. So that means F is equal to 0. So that's a sort of sound conclusion. The question is also where this formula is valid. Well, we in fact did not suppose anything. You just have to have F from L1, nothing else. Rf is again in L1, and Fourier transform is defined on L1. And then again here. So this conclusion for R to be injective is valid on L1. That's a non-trivial. If you have an operator, it's a very sensible statement, injectivity. You may have injectivity on a dense space, but if you expand the operator by continuity, it may get some zero null space, some null space. Now that's not the case. This shows that R is injective on L1. So that's the second information we have. Injectivity, and even on a more restricted space, reconstruction. The next step would be to extend this identity to more general class of functions on which C01 is dense. We will let it open. But now let's look for the proof. Oh, I have to stop. I have to stop here. Okay. Well, let me stop then. And we will then produce the proof in the next hour. Let me look. Okay. Okay. 10 minutes.